You ever stop to think about the idea of balance? I don't just mean in your day-to-day life, but as like a fundamental rule of how the entire universe works. From the simple ingredients in a recipe to the incredible forces holding a star together, it turns out everything is governed by this really precise cosmic balancing act. Today, we're going to dive right into that act, and we'll see how the very same principle connects a simple chemical reaction to the unbelievable power locked away inside an atom. All right, so let's jump right in with a question that sounds kind of nuts. What could a simple baking recipe possibly have in common with a nuclear bomb? And the answer, believe it or not, is actually super elegant. Both of them are controlled by a really strict set of rules, a formula where every single piece has to be perfectly accounted for. One gives you a delicious cake, the other unleashes an almost unimaginable amount of energy. But both, at their core, hinge on this art of balance. So let's start in a place we all know, the kitchen. Or, well, maybe more like a chemistry lab for our purposes. You see, chemical reactions are basically just recipes. You take some ingredients, which we call reactants, you mix them together, and you get a final product. But there's a cosmic rule book they all have to follow, no exceptions. And that big rule, it's called the law of conservation of mass. This is a big one. It was figured out way back in the 18th century, and it's been a cornerstone of science ever since. All it really says is that in any closed system, matter doesn't just get created or destroyed. The atoms you start a reaction with are the exact same atoms you end up with. They've just been rearranged into new combinations, kind of like shuffling a deck of cards. Nothing ever just disappears. And that's why an unbalanced chemical equation isn't just messy, it's flat out impossible, scientifically speaking. An unbalanced equation is basically saying that atoms are either popping into existence out of nowhere or just vanishing into thin air, and that just doesn't happen. So our job is to be like the universe's accountants, making sure everything adds up. So how do we fix these things? These broken recipes. How do we make sure our chemical equations are following the law? Well, the good news is there's a pretty clear step-by-step way to get it done. It really just comes down to three main steps. First, you just write down the basic reaction. Then, step two, and this is the most important part, you start adding these little numbers called coefficients in front of the molecules. They're basically just multipliers. And you tweak them until the number of atoms for every single element is exactly the same on both sides of the arrow. Then finally, you just add a little note about whether they're solid, liquid, or gas. Okay, theory is one thing, but let's actually see how this works with a real example. So we've got tin oxide reacting with hydrogen gas to make tin and water. And right off the bat, you can see this thing is unbalanced. We have 2 oxygen atoms on the left, but only 1 on the right. That's the problem. Okay, so first things first, let's tackle that oxygen problem. To get 2 oxygen atoms on the right side, we can't just change the H2O formula. That would make it something other than water. So instead, we put a big 2 in front of it. Boom. 2 water molecules, now the oxygens are balanced, 2 on each side. But look what we did. By fixing the oxygen, we kind of messed up the hydrogen. Now we have 4 hydrogens on the right, but still only 2 on the left. That's okay though. This is all part of the process. We just pop back over to the left side and put a 2 in front of the H2, and now we have 4 hydrogens there too. And just like that, it all clicks into place. Let's do a final check. 1 tin on both sides? Yep. 2 oxygens on both sides? Check. 4 hydrogens on both sides? You got it. Perfect. The recipe is now totally correct, and the law of conservation of mass is happy. All right, so we've gotten pretty good at balancing the books when we're just, shuffling atoms around. That's chemistry. But what if we could go deeper? What if we could change the very atoms themselves? This is where we leave the everyday world behind and step into the seriously strange and powerful world of the nucleus. And I absolutely love this way of thinking about it. Doing a chemical reaction is like rearranging the furniture in a house. But a nuclear reaction, that's like changing the very walls and structure of the house itself. It's a completely different game. I mean, the difference here is just night and day. Chemical reactions are all about the outer electrons of an atom, and the energy changes are pretty small, relatively speaking. But nuclear reactions, they involve the very core of the atom, the protons and neutrons. You're not just rearranging atoms, you're literally turning one element into a completely different one. And when you do that, you release mind-boggling amounts of energy. So, to really get this, we've got to talk about something called an isotope. An element is defined by how many protons it has, but it can have different numbers of neutrons. Think of them as different versions of the same element. For example, every single uranium atom has 92 protons, but uranium-235 has fewer neutrons than uranium-238, and that small difference makes it way less stable and way more useful for nuclear reactions. And you know what's cool? Balancing these nuclear equations is, in a way, even easier. You just have to make sure two numbers add up on both sides. The mass number on top, that's protons plus neutrons, and the atomic number on the bottom, which is just the protons. Look at this example of uranium-234 decaying. On top, 234 becomes 230 plus 4. Simple. On the bottom, 92 becomes 90 plus 2. The math is simple addition, right? But what it represents, an element literally changing into another, that's incredible. So this whole new kind of balancing act, this changing of elements, it unlocks a power source that is just, it's almost impossible to wrap your head around. We are talking about the energy that fuels the sun and all the stars. And it all comes down to a tiny, tiny little quirk in the universe's accounting system. That weird little quirk is called mass defect. And here's what it is. If you were to take a nucleus, like a helium atom, and weigh it, it would actually weigh less than if you weighed its individual protons and neutrons separately and added them up. It's like some of the mass literally vanished. So where'd it go? Okay, so here's the secret. It's not actually gone. That missing mass has been converted directly into the energy that holds the nucleus together. We call it nuclear binding energy. And the amount of energy you get from that teeny tiny bit of mass, it's staggering. And this is the secret sauce. Einstein's famous equation, E equals mc squared. It tells us exactly how much energy we get. E is energy, m is that little bit of missing mass, and c is the speed of light. Now, the speed of light is already a ridiculously huge number, but you have to square it. That's why even a microscopic amount of mass can be converted into a truly colossal amount of energy. So check out this chart. This is the nuclear binding energy curve, and it shows you everything. The higher up an element is on this curve, the more stable its nucleus is. And see that peak right in the middle? That's iron. It's like the most stable, most comfortable atom in the universe. So really heavy elements, way over on the right, like uranium, can release energy by splitting apart and moving up toward that peak. That's fission. And really light elements on the left, like hydrogen, can release energy by smashing together to move up the curve. That's fusion. Both are just nature's way of trying to get to that stable sweet spot. So you can see this isn't just some abstract theory for a blackboard. This is the science behind technologies that have completely changed our world. By getting a handle on these rules of nuclear balance, we've figured out how to actually put this incredible power to work. So have a look at this. It's a diagram of a nuclear reactor. Deep inside, there's a controlled chain reaction of uranium fission, releasing all that energy we just talked about. And at the end of the day, all that incredible nuclear physics is used to do something really, really simple: boil water. That steam turns a turbine, and that generates the electricity that powers our cities. It's an amazing example of converting mass directly into usable energy.
And it's not just about making electricity. This stuff is everywhere. The predictable decay of things like carbon-14 works like a cosmic clock, letting us date ancient artifacts. In medicine, special isotopes can light up our insides from medical scans, or even act as tiny targeted weapons to destroy cancer cells. We've even become modern alchemists, using this knowledge to create brand new elements that don't even exist in nature.
So it all comes back to where we started, doesn't it? Balance. From that simple recipe where atoms have to be perfectly conserved, all the way to a reaction inside a star where mass itself is converted to energy, the fundamental principle is the same. Matter and energy are just two sides of the same coin, playing by a set of rules we're still trying to fully understand. It really makes you wonder, right? What other secrets is the universe hiding? Secrets we could unlock if we just figure out how to balance the next equation.